A piece of amber, an electron, hold a moment, where did it go? Oh, there it is. And salt. What do these three have in common? In this video, we're going to explore their fascinating connection and delve into the world of electrons, the tiny but highly significant particles. These three may seem unrelated, but in the world of science and physics, there's a connection that ties them together. The fundamental presence of electrons, as well as the concept of electrical charge and its involvement in the generation of static electricity. Our story begins with the ancient observation of static electricity. The ancient Greek word for amber is electron, and this term is where we derive the word electron. The ancient Greeks noticed that when amber was rubbed against certain materials, it gained the ability to attract lightweight objects like bits of straw. This effect was an early observation of static electricity, although the underlying mechanisms weren't fully understood at the time. Electrons, the tiny particles we're about to explore, play a crucial role in this phenomena. Fast forward to modern science, and we've identified electrons as the subatomic particles responsible for carrying electric charge. The electron, discovered in 1897, is at the heart of understanding the atomic world. It is essential for comprehending topics like chemical bonding, leading to the creation of molecules, the enigmatic realm of quantum mechanics, and even the structure of the periodic table of elements. The behavior of electrons, their flow, and interactions with other charges are central to the field of electromagnetism. By the way, if you'd like to stay updated, feel free to subscribe, share, or leave your thoughts in the comments below. Now let's examine salt, which might surprise you. Salt, or sodium chloride, is in fact a chemical compound composed of sodium ions and chloride ions. Here's where electrons come into play again. These ions are formed when electrons are transferred between sodium and chlorine atoms. Sodium loses an electron, becoming a positively charged ion, while chlorine gains an electron, becoming a negatively charged ion. The attraction between these opposite charges leads to the formation of the ionic bond that holds the sodium and chloride ions together in a crystal lattice structure, forming the salt molecule. So, even in seemingly ordinary substances like salt, electrons play a crucial role in the formation of molecules, showcasing their significance in the atomic world. In my previous video, Atom, what it actually is, we explored the intricate structure of atoms, their profound significance, and their impact on our world. Today, we'll take a journey as we focus specifically on the unsung heroes of the atom, electrons, and discover their crucial role in shaping the very fabric of our universe. It's crucial to pay close attention because what we're about to discuss is essential, and every sentence holds the key to understanding the topics of my upcoming videos. But what exactly is an electron, and why is it so important? Let's dive right in, explore what they are, and discover some fundamental traits of electrons. Electrons are fundamental subatomic particles. The word electron is a combination of electric and ion. An electron is denoted as E- or beta-. Electrons are one of the primary components of atoms, and they orbit around the central nucleus, which contains positively charged protons and electrically neutral neutrons. The nucleus of the ordinary hydrogen atom deviates from this pattern as it consists solely of a single proton without any neutrons. As electrons traverse this arrangement, they generate an expansive, negatively charged cloud that fills almost the entire of the atom's volume. By 1914, key experiments conducted by physicists like Ernest Rutherford, Henry Moseley, James Franck, and Gustav Hertz has outlined the basic structure of an atom. A dense nucleus with positive charge at its center, surrounded by electrons of lower mass. Electrons belong to the category of subatomic particles known as fermions. Inside the subgroup of fermions, electrons can be more specifically characterized as leptons, and they are part of the lepton particle family's first generation. Leptons differ from quarks in that they don't experience strong interaction, which is responsible for binding protons and neutrons together within the atomic nucleus. Electrons are considered elementary because they lack known components or substructure and are considered point-like particles, although some scenarios in condensed matter physics involve their separation into three independent quasi-particles: spinons, orbitons, and holons or chargons. Electrons were the first subatomic particles to be identified. They were theorized in the late 19th century by the Irish physicist George Johnstone Stoney in 1874. Stoney initially referred to these units as electrolions in 1881, but later adopted the term electron to describe these elementary charges, which later became a fundamental concept in physics. Electrons were discovered by the British physicist Sir Joseph John Thomson during his cathode ray tube experiment on April 30 of 1897. Electrons have a charge of approximately minus 1.602 times 10 to the 19 coulombs, which is considered negative. The Coulomb force between electrons and protons within atoms allows for the formation of atoms. In a neutral atom, the quantity of electrons matches precisely with the number of positively charged protons. However, some atoms can possess an excess or deficiency of electrons relative to their protons, resulting in an overall negative or positive charge for the atom. These charged atoms are referred to as ions. Furthermore, not all electrons are bound to atoms. Some exist independently in a free state, often accompanying ions in a state of matter referred to as plasma. The electron's radius is a complex problem in theoretical physics. Theoretical considerations suggest a point-like electron, while experimental measurements suggest an upper limit of 10 to the power of minus 22 meters. While electrons contribute to the overall charge of an atom, their mass is relatively insignificant. In terms of mass, electrons are much lighter than protons and neutrons. A proton has a mass of approximately 1.673 times 10 to the minus 27 kilograms. Neutrons also have a mass of approximately 1.675 times 10 to the minus 27 kilograms. Electrons have a mass of about 9.109 times 10 to the minus 31 kilograms, which is 1,836 times lighter than protons and neutrons. Consequently, electrons are regarded as massless, and their mass is not factored into the calculation of an atom's mass number. The electron is considered stable on theoretical grounds with an experimental lower bound for its mean lifetime estimated at 6.6 times 10 to the 28 years. Electrons' lightweight nature allows them to move more freely around the nucleus. This mobility is a key factor in chemical reactions and electricity. In 1913, Danish physicist Niels Bohr introduced a groundbreaking idea. He proposed that in an atom, electrons can only exist in specific energy levels which are quantized. The Bohr model of the atom depicts a nucleus at the center, surrounded by three concentric circles representing electron orbits. These specific orbitals are often depicted as shells or clouds and have distinct energy levels. Electrons occupy these energy levels based on their energy, with the lowest energy levels closest to the nucleus. This means they can jump between energy levels by absorbing or emitting discrete packets of energy with specific frequencies known as photons when accelerated. Bohr's model successfully explained the spectral lines of the hydrogen atom, but faced limitations in explaining the intensities of these lines and more complex atoms. In 1924, French physicist Louis de Broglie proposed that all matter, including electrons, could exhibit both particle-like and wave-like properties. This idea suggested that electrons could exhibit both particle-like and wave-like properties under specific conditions. This property is demonstrated in the double-slit experiment. They can collide with other particles and diffract like light. This duality is described by quantum mechanics and is essential to understand electron behavior, especially in the context of the electron cloud model. Their wave properties are easier to observe in experiments than those of other particles like neutrons and protons due to their lower mass, resulting in longer de Broglie wavelengths for a given energy. In this first part of our exploration of electrons and their crucial role, we've delved into the fascinating world of electrons, from their historical significance in the observation of static electricity to their pivotal role in modern science and technology. We will continue the journey in the second part, where we'll explore even more about these remarkable particles, from their role in chemistry to their involvement in electricity and quantum mechanics. So stay tuned for the next installment and let's uncover more about the world of electrons. See you in the second part.